In this video we will show how to answer the question, provide an unambiguous grammar, G, for the language L, where L is a set of strings W over the alphabet AB, and the number of A's in W is equal to the number of B's in W. So we will actually do this question in two parts, so two videos. This video we will show how to come up with a good candidate grammar by doing a couple of different grammar examples, and in the following video we will show how to prove candidate grammar is unambiguous. So first, let's list some strings in the language of the grammar that we're trying to create, the language L that we're trying to create, so that we have a starting point to work from. So these will be strings in L. And notice that since the number of A's has to equal the number of B's, the length of the string is necessarily even. So if we try strings of length 2, we would have AB. We would also have BA. That's all of the strings we can have of length 2. Length 4, we have a few more. We have AABB, BBAA, ABBA, BAAB, ABAB, and BABA. And this should, I think, be all of them. Let's see. Looks like it. Okay. So, and then this list would continue on infinitely, so I'm not going to make an infinite list. But let's try a first grammar. So let's call this grammar G1. And if we're just thinking about having the number of A's equal the number of B's, we might try something that looks like this. So S will be our starting variable, and it could make A or BSA or epsilon. Okay, so let's test this first grammar. What can we make? We can make AB. We can make BA, right? Just by using one rule, we can make each of those. Let's try using two rules. If I use the first rule followed by the first rule again, so we'll make a derivation down here so we can see what's happening. S goes to ASB, and then I'm going to use the first rule again, so ASBB, and then let's get rid of that S, AABB. Okay, so I can make that one, AABB. If I take the first rule, so I'm just going to claim here that if I did the same thing with the second rule, using the second rule twice, I would get just the opposite string with the B's and the A's swapped. Okay, so let's try using a mix of the first and the second rule. So I could use ASB as the first rule, and then I'm going to use the second rule. So I end up with A, replace S with BSA, and then I have this trailing B that I still had left. And then if I replace that S with epsilon, I'm going to get ABAB. Okay, so ABAB, and I claim that if I use the second rule followed by the first rule, I'm going to get the same thing with the B's and the A's swapped, BA, BA. Okay, so this has covered quite a few of our strings that we've been that we've selected to test. But if we notice, each one of these strings has the first and last symbol are different. So we might ask, can we make the string AABB? Okay, so let's try to make AABB. So I would do S goes to, is that what I wanted to do? Oh, I already made that one. Just kidding. Go back to what I actually said. Okay, I want to make the string ABBA. I want to make a string where the first and last symbol are the same. Okay, so if I want to make ABBA, then I need to take a rule that has A as the first symbol and A as the last symbol, and I don't have a rule like that. Okay, so I claim I can't make that one. If we try, we get something like this, and now there's no way to get an A on the end, right? All of our replacements are going to happen here on the inside. Okay, so this grammar can't make W equal to W0, W1, so this is the substrings of the grammar, of the substrings of the string. Can't make a string like this such that W0 is the same as Wn. Okay, so that's what we're seeing here. We can't have a string that the first symbol and the last symbol is the same symbol. So this does not actually create, this won't generate all the strings in L. So this grammar doesn't work. So let's think about the problem. The problem was, once I took the first rule, like here, I couldn't build on it over here. Okay, and so we might be tempted to say, well, introduce a rule of the form S goes to ASA, right? That would solve that problem. I would get some strings where the first and the last symbol are both A's, but I violate the property that the number of A's and B's are the same. Because, for example, I could then take the rule epsilon, this is now a derivation, and make AA. Okay, and this is not in the language. So that's not a solution. Instead, let's try a second grammar. So I'm just going to jot down the strings again real quick. Okay, so these were our subset of strings that we're trying to create. So if we try a second grammar, let's call it G2. And remember, the problem was, once I make this chunk, in our previous grammar, this character and this character differed. So I wanted to be able to make another chunk where this character and this character are the same. Okay, that was the problem. So let's try adding a new rule that allows us to make two chunks. That seems like a good idea, right? Okay, so we've just added a rule. We haven't taken any rules away. So we are definitely going to be able to create all of the strings that we had before. So we had this string, we showed this string and this string. And then, did we show this string and this string? I think we did. Yes. Yes, okay. So we're really focusing on these two here. So I claim that we can make those now. So if we do a derivation, S goes to SS, and then we handle the first chunk with, so I'm going to replace this one. So this will be a leftmost derivation. If I replace that one with ASB, okay, leftmost derivation, let me do this one now. What am I trying to make? I'm trying to make ABBA. So I'm going to replace that with epsilon. Now I'm looking at this variable, and I'm going to use the rule BA, or BSA. Okay, now I need to replace this one, ABBA. Okay, and it's pretty easy to see that if I had used the rules in a different order, I'd also get BAAB, right, because all these rules are symmetrical. Okay, so I can get these two. So this looks pretty good, right? It appears that we have a grammar that will generate strings where the number of A's and B's are equal, because every time we make a terminal A, we're making a terminal B. And it also appears to be the case that we can make rules where the first and last symbol are different and where the first and last symbol are the same. And so if we kept doing this, I'm fairly confident we could prove that this generates all of the strings in the language. However, the question is to provide an unambiguous grammar. So now we need to ask the question, is G2 ambiguous? Okay, and how do we prove that something is ambiguous? To prove the grammar is ambiguous, we can do one of two things. They both work. We can show that there exists a string W generated by G that has two or more leftmost derivations, or we could also show that the same string W or another string W, any string generated by the grammar, has two or more different parse trees. Okay, so these are equivalent. Let's see if we can find a string in this that has a derivation from this grammar that has either two leftmost derivations or two different parse trees. Okay, so let's try the string. So we're going to let W equal AB, AB, and we're going to ask, does W have two or more leftmost derivations? Okay, so let's try using the rule. Let's try using let's try not using our new rule first. Let's try using our old grammar, G1. Okay, so remember G2 is just an extended grammar of G1. Okay, so let's call this derivation 1. Okay, so using the old rules, we could do ASB, and then replacing S, we would get A, and now we need to make the BA in the middle, so let's do BSAB. And then replacing S again, we get ABAB. Okay, so each time this is what I'm replacing. Okay, so there's 1. Let's call this derivation 2. In this one, let's use the new rule. So let's use S goes to S. So here we could do, let's replace, it has to be leftmost, so we have to replace the left S first. So let's replace it with A. So what do we want here? We're considering making the left chunk, the first half, if you will, so we want to make AB. So if we do ASB, and then here's our trailing S. Now I need to replace this S. I'm going to use epsilon, so I'm going to use ABS. Okay, now this is the leftmost variable, so I need to replace that one. And again, we're going to use the ASB rule, so we have AB, ASB. Now this is my leftmost variable, and then AB, AB. Okay, so we have two different derivations for the same string. And these correspond to two different parse trees. So just for fun, let's draw the parse trees. Okay, let's call this P1, parse tree 1 for derivation 1. So what does it look like? It has S as the root, it has our start variable as the root. And what does S generate? It's going to generate A as a terminal, so it's a leaf, and then S, and then B is another leaf. Then we replaced S with B, S, A. And then we replaced S with epsilon. Okay, and if we read along the leaves, we get A, B, A, B. Okay, let's call this P2 for derivation 2. So we still have S as our root, our start symbol. And then here, S gets replaced, or generates, SS. The first S generated A, S, B. Okay, and then we replace that S by epsilon. The second S generated A, SB, and then we replaced S by epsilon. So if we read along the leaves, again we get AB, AB. Okay, so we see two different parse trees corresponding to two different leftmost derivations for the same string AB, AB. So while this grammar, G2, should generate all of the strings in L, it's not unambiguous. It is ambiguous. We have proved that it is ambiguous. Okay, so let's introduce grammar that we claim is unambiguous. Am I out of pages? I am out of pages. We'll put it down here. Okay, so let's try the grammar E, so this will be G3. E goes to A, B, E, or B, B, A, E, or epsilon. A goes to A, B, A, or epsilon. B goes to B, oh, yeah. B goes to B, B, A, B, or epsilon. Okay, so note that the kind of rules we have here are very similar to the kind of rules that we had before. If we needed to make AB, AB, like we have above, we could do, we could take the first rule, A, big A, little b, E. We could replace that A with epsilon, and then we could replace the E by that same rule again. A, big A, B, E. So let's do that one real quick. I need more room. It's okay. So the derivation would look something like E goes to A, B, E, goes to A, B, E. So doing leftmost, that's going to yield A, B. We replace with A, B, E. And that yields, if we replace the A by epsilon, A, B, E. And then if we replace the E by epsilon, we end up with A, B, AB. Okay, so note that there shouldn't be, we're claiming that there isn't another leftmost derivation of this string, because in this step here, where we had to replace the leftmost variable, there isn't a rule that I can get from that variable. So if we look down at the rules that A has, rules for variable A, the only rule I can take there is to insert an AB in place of that A. Okay, so what would I get if I did that? I'd get AA, BB. Okay, I can't get AB, AB. Alright, so this should give us some indication that this is a good candidate grammar for being unambiguous. However, when we wanted to prove that the grammar was ambiguous, all we had to do was come up with two leftmost derivations, or two different parse trees. Here, just saying for this particular string there isn't an additional leftmost derivation isn't good enough, because then the question would be, well, is there a string? And so you could say, okay, let me take another string. Okay, this one doesn't have 2 leftmost derivations. And then we would say, okay, how about the next string? So if the language is infinite, you would have to do this for an infinite number of strings to prove that none of them have 2 leftmost derivations. And clearly, this is not possible, right? We can't do something like this for an infinite number of strings. No matter what, you'd say, well, I've done 10 million strings, and I'd say, well, how about the 10 million in first one? Maybe that one has 2 leftmost derivations. So instead, what we need to do is prove that it's not possible for any string to have 2 leftmost derivations or 2 different parse trees. Okay, so we will do that in the next video.